Welcome to the Nocturnal Astronomer. I am your host, Atlas Reid, and tonight we are journeying through the story of one of autumn's most captivating celestial performances, the Leonids meteor shower. Each November, as the nights grow longer and the air turns crisp, Earth passes through a stream of ancient debris left behind by a wandering comet. What follows is a gentle rain of light across our skies, meteors streaking at speeds that would make your fastest jet fighter look like it is standing still. The Leonids are not just another meteor shower. They carry with them a history that has shaped human understanding of the cosmos itself. These shooting stars once fell so abundantly that witnesses believed the heavens themselves were unraveling. They inspired scientific revolutions, appeared in the journals of abolitionists and presidents, and reset the calendars of entire nations. Tonight, we will explore what makes these meteors special, why they occasionally erupt into spectacular storms, and how a small, icy wanderer named Tempel-Tuttle orchestrates this annual dance of light. Picture yourself standing beneath the dark November sky. The constellation Leo the Lion rises in the east around midnight, its distinctive backward question mark of stars marking the lion's mane. From this point in the heavens, meteors begin to streak outward in all directions, each one a tiny fragment of rock and ice meeting its brilliant end as it collides with our atmosphere at 44 miles per second. That is over 200 times faster than a rifle bullet. At such incredible speeds, these specks, some no larger than grains of sand, create flashes bright enough to cast shadows and leave glowing trails that linger like cosmic brushstrokes across the night. The Leonids typically produce around 10 to 15 meteors per hour at their peak, a modest display compared to some of their celestial cousins. But approximately every 33 years, something extraordinary happens. The shower transforms into a storm, and the sky erupts with thousands upon thousands of meteors. In 1966, observers in the southwestern United States witnessed 40 to 50 meteors every single second during a 15-minute window. The meteors fell so densely that witnesses described feeling as though Earth itself was moving through space, plowing through an invisible river of debris. Some said it looked like rain, but instead of water, the sky poured light. These are not random occurrences. They are the product of precise celestial mechanics, a cosmic clockwork involving the orbit of a comet, the gravity of giant planets, and Earth's annual journey around the Sun. Understanding the Leonids means understanding how our solar system works, how comets shed their outer layers, and how we can predict celestial events with remarkable accuracy. If you enjoy these types of videos about the night sky and its wonders, please consider giving this video a thumbs up and subscribing to the Nocturnal Astronomer. It helps me continue bringing you these nighttime explorations of our cosmos. And here is something I would love to hear from you. Have you ever seen a meteor shower? What was your first thought when you saw a shooting star streak across the sky? Let me know in the comments. I find people's first impressions of these cosmic moments absolutely fascinating. Let's dive in. Every meteor shower has a parent, and for the Leonids, that parent is Comet 55P Tempel-Tuttle, a small world of ice and rock measuring just over 2 miles across. That may sound substantial, but in cosmic terms, it is tiny. You could fit this comet comfortably within the borders of many small cities. Yet despite its modest size, Tempel-Tuttle creates one of the most famous meteor showers in our skies. This comet travels in a long, stretched orbit around the Sun, taking approximately 33 years to complete a single revolution. Think of it as a cosmic pendulum, swinging from the frigid outer reaches of the solar system, where it spends most of its time frozen and dormant, down to the inner solar system where the Sun's warmth awakens it. At its farthest point, Tempel-Tuttle ventures nearly 20 times farther from the Sun than Earth does. Out there, in that cold darkness, the comet is essentially a frozen ball, inactive and silent. But every 33 years, Tempel-Tuttle swings back toward the sun, crossing inside Earth's orbit at a distance slightly less than our own distance from our star. As it approaches, something magical happens. The sun's radiation begins to warm the comet's surface. Ice that has been frozen for decades starts to vaporize, transforming directly from solid to gas. This process releases dust and rocky particles that have been locked inside the comet since the solar system's formation over 4.5 billion years ago. Imagine unwrapping a package that has been frozen in time for billions of years. That is essentially what happens when a comet approaches the sun. The ice acts as a preservative, and when it evaporates, it releases pristine samples of the solar system's earliest days. These particles, ranging in size from fine dust to pebbles, get pushed away from the comet by the pressure of sunlight and the solar wind. They do not simply scatter randomly into space. Instead, they follow the comet's orbital path, creating a river of debris that stretches along the entire orbit. Here's where Earth enters the story. Our planet orbits the sun once every year, following its own predictable path through space. Every November, Earth's orbit intersects with the orbit of Tempel-Tuttle. When this happens, we pass through the debris stream the comet has left behind. It is like driving through a tunnel during a rainstorm. Even though the rain is falling all around the tunnel, you only get wet when you enter the open air. Similarly, meteor showers only occur when Earth passes through these cosmic debris streams. Tempel-Tuttle has a special characteristic that makes its meteor shower particularly impressive. The comet travels in what astronomers call a retrograde orbit. This means it orbits the sun in the opposite direction compared to Earth and most other planets. When Earth encounters Tempel-Tuttle's debris, we are essentially having a head-on collision with these particles. This explains why Leonid meteors are among the fastest meteors we see, entering our atmosphere at 71 kilometers per second. The comet was discovered twice, independently, within a year. German astronomer Ernst Tempel spotted it in December 1865, and American astronomer Horace Tuttle found it again in January 1866. Neither knew initially that they had found the same object. After astronomers calculated its orbit and determined its 33-year period, they realized this comet was responsible for the Leonid meteors that had been observed for centuries. The comet became known by both their names, a fitting tribute to independent discovery. Tempel-Tuttle last passed closest to the sun in 1998 and will return again in 2031. When you watch a meteor shower, you might notice something curious. The meteors do not appear randomly scattered across the entire sky. Instead, if you trace their paths backward, they all seem to originate from a single point. Astronomers call this the radiant point, and for the Leonids, this point lies within the constellation Leo the Lion. Understanding the radiant is key to understanding why meteor showers behave the way they do. Imagine standing on railroad tracks and looking down the rails toward the horizon. The tracks appear to converge at a distant point, even though you know they remain parallel. This is an optical illusion created by perspective. The same principle applies to meteor showers. The debris particles are actually traveling on parallel paths through space, but from our viewpoint on Earth, they appear to diverge from a single point. The Leonids get their name from their radiant point's location in Leo. Specifically, the radiant sits near the star Algeba, which marks part of the distinctive backward question mark pattern called the sickle. This asterism represents the lion's head and mane in the constellation. When Leo rises in the eastern sky around midnight in mid-November, the radiant rises with it. As the night progresses and Leo climbs higher, the radiant reaches its highest point around dawn. This timing is not coincidental. Meteor showers are generally best viewed in the hours before dawn because of how Earth moves through space. Our planet does not simply sit still while meteors rain down upon it. Earth is orbiting the Sun at about 67,000 miles per hour. Think of Earth as a car driving through a snowstorm. The front windshield of the car gets hit by more snowflakes than the rear window because the car is driving into the snow. Similarly, the side of Earth that faces forward in our orbital motion, which happens to be the side experiencing morning hours, encounters more meteors than the trailing side. When you watch for Leonids, you should not stare directly at Leo. This might seem counterintuitive, but meteors appearing closest to the radiant have the shortest apparent trails because they are traveling almost directly toward you. Think about watching a plane flying overhead. When it flies directly above you, it appears to move slowly across a small patch of sky. But when it is closer to the horizon, it appears to streak across a much larger portion of the sky. The same principle applies to meteors. The most spectacular Leonids, those with long, brilliant trails, appear farther from the radiant. The radiant point is not fixed relative to the stars. As Earth moves along its orbit, the angle at which we encounter the debris stream changes slightly. This means the radiant's position shifts a bit each night during the shower's active period, which runs from early November through early December. However, the shift is subtle, and the radiant remains firmly within Leo throughout the shower's duration. Leonid meteors are particularly striking because of their speed and color. At 71 kilometers per second, they rank among the fastest meteors visible from Earth. This high velocity creates intensely bright trails. Many Leonids display vivid colors, particularly blue and green hues, caused by the specific elements vaporizing as the meteoroid burns up. The chemical composition of Tempel-Tuttle's material determines these colors. When meteoroids contain certain elements like magnesium and calcium, they produce characteristic colors as these elements emit light at specific wavelengths while burning in our atmosphere. The trails left by Leonid meteors can persist for several seconds, sometimes even minutes. These lingering trails, called persistent trains, occur when the meteoroid's passage through the atmosphere ionizes air molecules, creating a glowing tube of plasma that slowly dissipates. On particularly active nights, these trains can accumulate, creating ghostly streaks across the sky. On the night of November 12th to 13th, 1833, the sky over North America erupted in a display that would forever change how humanity understood meteors. The Leonids produced what remains one of the most spectacular meteor storms ever witnessed, with estimates ranging from 100,000 to well over 200,000 meteors visible during a 9-hour period. People woke their neighbors. Church bells rang in the darkness. Many believed they were witnessing the end of the world. Accounts from that night described the meteors falling like snowflakes or rain. One witness wrote that heaven seemed wrapped in splendid fireworks, as if every star had been suddenly hurled from its course and sent lawless through space. The display was visible from Canada to Mexico, from the Atlantic Ocean to the Pacific. It occurred at a time when there were no electric lights to wash out the stars, when the moon had already set, providing perfect viewing conditions. The November darkness made the meteor storm appear even more dramatic. The 1833 Leonid storm had profound effects beyond the visual spectacle. Native American nations, including the Cheyenne and Lakota, marked their calendars by this event. Many people calculated their birthdays in reference to the night the stars fell. The event appeared in the personal accounts of historical figures including Harriet Tubman, Frederick Douglass, Abraham Lincoln, and Joseph Smith. Newspapers across the continent carried articles about the phenomenon, rising above typical partisan debates to document what they had witnessed. From a scientific perspective, the storm was revolutionary. Before 1833, the prevailing view held that meteors were atmospheric phenomena, like lightning or rain. They were thought to be created by gases rising from Earth itself. But the 1833 storm was too vast, too coordinated to be explained by local atmospheric effects. It demanded a different explanation. American astronomer Denison Olmsted took up the challenge. He spent weeks after the storm collecting accounts from across North America. In January 1834, he presented his findings, noting several crucial observations. First, the shower lasted only a few hours and was not seen in Europe, indicating it was tied to specific timing and geography. Second, all the meteors appeared to radiate from a point in the constellation Leo. Third, the meteors were traveling at tremendous speeds, which he calculated, though his initial estimate proved too low. Olmsted proposed a revolutionary idea. The meteors, he suggested, originated from a cloud of particles in space. Earth, in its orbit around the Sun, had passed through this cloud. The meteors were not atmospheric phenomena at all. They were extraterrestrial, visitors from beyond our world burning up as they encountered our atmosphere at immense speeds. This insight marked the birth of meteor astronomy as a scientific discipline. But Olmsted could not explain everything. He did not know about Comet Tempel-Tuttle, which would not be discovered for another 3 decades. He could not explain why the meteor storm happened in 1833 specifically. The full picture would only emerge over the following decades as astronomers discovered the comet, calculated its orbit, and realized it matched the orbit of the Leonid meteors. The 1833 storm was actually caused by debris that Tempel-Tuttle had released during its 1800 passage near the Sun. The particles took 33 years to spread around the orbit and be in the right place for Earth to encounter them. This discovery led to predictions of future storms. When another impressive Leonid display occurred in 1866, 33 years after the Great Storm, it confirmed the pattern. Scientists predicted another storm for 1899, 33 years later. That prediction failed, and the disappointment was profound. Many felt astronomy had suffered its worst blow ever in the eyes of the public. The heavens, it seemed, were more complicated than anyone had imagined. For nearly 7 decades after the disappointment of 1899, the Leonids remained relatively quiet. Small outbursts occurred in 1900 and 1901, but nothing approaching the storms of 1833 or 1866. Many astronomers believed the meteor storm phenomenon had ended, that perhaps the debris had been scattered too widely by planetary gravity to produce intense displays anymore. Then came 1966. On the morning of November 17, 1966, observers across the southwestern United States and Hawaii witnessed something extraordinary. For 15 minutes, meteors fell at a rate of 40 to 50 per second. That translates to between 2,400 to 3,000 meteors per minute. The sky blazed with light. Witnesses described feeling a visceral sense of Earth's motion through space, a rare moment when humans could perceive our planet plowing through the solar system. The 1966 storm was not as long as the 1833 event, but its intensity during that 15-minute peak may have been even greater. The following morning, November 18th, observers in East Asia and Australia saw their own intense display as Earth continued through the debris stream. Scientists now had modern instruments to study the event. Radar observations revealed that the densest part of the meteoroid stream was remarkably narrow, just 35,000 kilometers wide. Earth swept through this filament of debris in only 1 hour. The 1966 storm reignited scientific interest in the Leonids. Astronomers began developing more sophisticated models of how meteor streams evolve over time. They realized that when a comet approaches the sun and releases material, that material does not spread out uniformly. Instead, it forms narrow trails that follow the comet's orbit but can be shifted by solar radiation pressure and planetary gravity. Earth might pass near Tempel-Tuttle's orbit every year, but to produce a storm, we need to pass directly through one of these narrow, dense trails. This understanding led to a breakthrough. Different trails come from different passages of the comet. The 1833 storm was caused by material released by Tempel-Tuttle during its 1800 orbit. The 1866 storm came from the 1733 trail. The 1966 storm originated from debris released in 1899. This explained why the 1899 prediction had failed. The comet passed by in 1899, but its fresh debris had not yet had time to spread into Earth's path. We would not encounter that material until 1966. As the comet returned in 1998, astronomers made detailed predictions about potential storms in 1999, 2000, 2001, and 2002. Unlike their predecessors a century earlier, they had powerful computers to calculate exactly where each debris trail would be and when Earth would intersect them. The predictions proved remarkably accurate. Significant outbursts occurred in 1999 and 2001, though they did not match the intensity of 1966. In 2002, the last major outburst of that cycle occurred. The storms did not produce the apocalyptic rates of 1833 or 1966, partly because Jupiter's gravity had perturbed some of the debris trails. The giant planet acts like a gravitational shepherd, nudging orbits whenever the debris passes nearby. Sometimes this scatters material away from Earth's path. Other times it can concentrate material, potentially creating future storm conditions. Modern meteor science represents a triumph of prediction and understanding. We can now forecast meteor shower activity with impressive accuracy. We know which comet produces which shower. We can calculate when major outbursts might occur, though predicting the exact intensity remains challenging. The Leonids transformed from mysterious celestial portents into understood phenomena, their behavior governed by the same gravitational laws that keep planets in their orbits. Watching the Leonids requires patience, preparation, and the right expectations. Unlike pictures of meteor showers that compress hours of activity into single images showing dozens of trails, real-time meteor watching is a waiting game punctuated by brief moments of excitement. In most years, you might see 10 to 15 Leonids per hour at the shower's peak, which means roughly one meteor every 4 to 6 minutes. The magic comes not from constant action, but from the anticipation between meteors and the surprise when a particularly bright one streaks across the sky. The shower is active from early November through early December, but peaks around November 17th or 18th each year. The best viewing window is after midnight until dawn, when the radiant in Leo climbs higher in the eastern sky. You want Leo to be as high as possible because higher radiant means meteors have more atmosphere to travel through, creating longer, brighter trails. The hours just before dawn typically provide the best show. Finding a dark location is crucial. Light pollution washes out all but the brightest meteors. The difference between viewing from a city and viewing from a truly dark site is dramatic. From a city, you might see a handful of the brightest Leonids. From a dark site, you will see the full spectrum of meteor brightness, including faint ones that would be invisible against light-polluted skies. The dark adapted human eye is remarkably sensitive. Give your eyes at least 20 minutes to adjust, avoiding all white light during that time. Red light preserves night vision, so if you need illumination, use a red flashlight. Dress warmer than you think necessary. November nights can be brutally cold, and meteor watching involves sitting or lying still for extended periods. Your body generates less heat when stationary, and you will be staring upward, exposing your face and neck to the cold air. Bring blankets, sleeping bags, hand warmers, hot beverages. Comfort is not a luxury when meteor watching. It is a necessity. If you are cold and miserable, you will not stay out long enough to see many meteors. A reclining lawn chair or blanket on the ground works better than standing. You want to be able to see as much sky as possible without straining your neck. Some meteor watchers prefer lying on their backs, looking straight up. This position provides the widest field of view, though it can be hard on the back after a while. Find what works for you. The key is comfort and a clear view of a large portion of sky. Do not look directly at Leo. While the meteors radiate from the constellation, they are visible across the entire sky. In fact, meteors appearing far from the radiant often display longer trails because of perspective effects. Let your eyes wander across the sky. Soft focus works better than concentrating on a single area. Your peripheral vision is actually more sensitive to motion than your direct vision, so you might notice meteors at the edge of your sight before you see them head-on. Leonid meteors are distinctly fast and often colorful. When you see one, note its color and how long the trail persists. The fastest meteors create intense trails that can linger for several seconds. Particularly bright meteors, called fireballs, might cast shadows or even leave persistent trains that glow after the meteor has vanished. These trains can last minutes, slowly drifting and dissipating. Patience is perhaps the most important tool for meteor watching. You might see 3 meteors in 5 minutes, then none for 20 minutes. Do not be discouraged. The anticipation is part of the experience. Many veteran meteor watchers find that the quiet periods under dark skies, watching stars slowly wheeling overhead, provide their own rewards even apart from the meteors themselves. The Leonids have been observed for over 1,000 years, making them one of the oldest documented meteor showers. Chinese astronomers in 902 AD described stars falling like rain during November of that year, the earliest confirmed record of Leonid activity. These ancient observers could not have known they were watching debris from a comet that orbits the Sun every 33 years. To them, the meteors were mysterious, possibly divine messages written across the night sky. European accounts from 1630 describe unusually large numbers of meteors appearing 2 days after the death of Johannes Kepler, the great astronomer who discovered the laws of planetary motion. Some authorities of the time saw this as a celestial salute to Kepler from the heavens. In 1766 and 1799, observers in South America reported spectacular meteor displays in November. German scientist Alexander von Humboldt witnessed the 1799 event from what is now Venezuela. He described thousands of fireballs and falling stars falling in succession for 4 hours, many as bright as Jupiter, leaving long smoke trails behind. These historical accounts, compiled and analyzed over centuries, eventually revealed the 33-year pattern. Even before astronomers understood what caused the shower, observers noticed it seemed to recur in cycles. The pattern was there in the historical data, waiting to be discovered. When Denison Olmsted investigated the 1833 storm, he began the systematic collection of meteor shower data that would eventually unlock the mystery. The discovery of Comet Tempel-Tuttle in 1865 and 1866 provided the missing piece. Astronomers quickly calculated the comet's orbit and realized it matched the Leonids' path through space. The comet's 33-year period explained the shower's cyclical nature. For the first time, humanity understood the physical mechanism behind meteor showers. They were not atmospheric phenomena, but the result of Earth passing through debris streams left by comets. This understanding enabled prediction. When the next major Leonid displays occurred in 1866, 1867, and 1868, they confirmed the connection. The failed prediction for 1899 taught astronomers that the relationship between comets and their meteor showers is complex. The comet's presence does not guarantee a storm. The debris must be in the right place at the right time, and gravitational perturbations from planets can shift material away from Earth's path. The 20th century saw tremendous advances in understanding meteor streams. Radar observations during and after World War II allowed scientists to study meteors in daylight and cloudy conditions, building a more complete picture of shower activity. Computer models in the later 20th century enabled precise calculations of how debris trails evolve over centuries. Predictions became sophisticated enough to forecast not just which years might produce storms, but specific times when enhanced activity might occur. The Leonids played a crucial role in developing this understanding. Because their parent comet has such a well-known orbit and because historical records document their activity over so many centuries, the Leonids became a test case for meteor shower prediction models. Success in predicting Leonid activity in the late 1990s and early 2000s validated these models and led to improved predictions for other meteor showers. Looking ahead, astronomers expect the Leonids to remain relatively modest for the next several decades. The next opportunity for storm-level activity might not occur until the middle or late 21st century, depending on how planetary perturbations affect the debris trails. Jupiter's gravity, in particular, can significantly alter the position of meteoroid streams over time. Some debris might be pushed into Earth's path, while other material might be scattered away. And on that note, we have completed our journey through the story of the Leonids, from the ancient debris of a small comet to the brilliant streaks of light that grace our November skies. Thank you for joining me on this exploration of mid-November's shooting stars. This is Atlas Reid, your host at the Nocturnal Astronomer, reminding you to look up and appreciate the cosmic dance happening above us. Until next time, may your skies be dark and your curiosity endless.